In this video, I want to have a look at proofs by induction that involve inequalities. So we're going to run through one example, and it's asking us to prove that 3 to the power of n is greater than or equal to 2n plus 5 for all our integers where n is greater than 1. So just keep in mind that it is a greater than, not a greater than or equal to. So that means when we test our first value, we're actually going to test n equals 2. So we're going to prove true or show that it's true for that first value. So show true for n is equal to 2. So that means we're just going to substitute 2 in. So our left-hand side would be 3 to the power of n, so 3 to the power of 2, which is 9. And for our right-hand side, we're going to have 2 times n, which is 2, plus 5. So that would be 4 plus 5, which is 9. So because the left-hand side does equal the right-hand side, and we wanted it to be greater than or equal to, we can write therefore true for n, getting confused, for n equals 2. All right, then we're going to go through and we're going to assume that it's true for n equals k. So that means we're going to assume that 3 to the power of k is greater than or equal to 2 times k plus 5. So we're assuming this, and we're going to use that in a moment. And then we're going to prove that it's true for n equals k plus 1. So that means we're trying to prove that 3 to the power of k plus 1 is greater than or equal to true outside of k plus 1 plus 5. All right, so let's have a look at this left-hand side. So the left-hand side is 3 to the k plus 1. Now we can split that up into 3 times 3 to the k, because that 3 there would have a 3 to the power of 1, and when we multiply things with the same base, we add the powers. So these two things are the same, so we've split this up. Now from our assumption, we know that 3 to the k is greater than 2k plus 5. So we can say that this statement, because of our assumption, this has to be greater than or equal to 3 outside of 2k plus 5. Now these proofs can be a little bit more complicated from your very basic ones. So to prove that we know this because of our assumption, next to this we're going to write using assumption. Or you can write from assumption as well, so we know where that piece of information's come from, where that substitution's come from. So we've replaced that, and we know that this expression here has to be less than this one. If we expand that out, then that line is going to be equal to 6k plus 15. And if we compare that to what we had up here, we could look just for a second, if I put over here, if I put my right-hand side, if I expand that out, I'd have 2k. I'd have 2k plus 2 and then plus 5, so I'd have 2k plus 7. So we want this term to be greater than this one. Now, if I've said that this expression is greater than this one here, then it also has to be greater than or equal to 2k plus 7, because 6k plus 15 has to be greater than 2k plus 7, because we know that k is always positive. So that means that it is greater than or equal to the right-hand side. So then we can say, therefore, true by induction for all n where n is greater than 1. All right, so that's having a look at a proof using induction that involves inequalities.